Switzerland. There's no sound? Oh, now it's better. And people from Ruhr-Universität Bochum in Germany, and UNIST in South Korea. So let's dive in. What are derived type confusion in C++? As you probably know, C++ is an object-oriented programming language, and it allows for inheritance. So you can define a class hierarchy, for example, parent-child, and then you can use a child as if it was a parent object. This allows for flexible and generic code because you define your function only once. It accepts a parent object, and you can use a child passed to it. Why can you do that? If you look on the right, there is a memory layout of a child object. It actually has the attribute of the parent object and the attribute of the child following. So when you pass this object to a function expecting a parent object, it can just read the start of the object. These upcasts are safe, but it raises the question, can we use a parent object as if it was a child? In C++, you can do that through an explicit cast operator, but the question is it safe? And sadly, it's not always the case. It is safe if you downcast back to the same object. So if you have a child object, you first upcast it to a parent object and then cast it back to a child. But if you have a child, cast it to a parent, and then use this parent object as if it was a sibling, this might lead to memory corruption. Why? If you look back on the right side of this slide, maybe the sibling object will have a larger size. Maybe it has extra attribute. When you try to access these attributes, you might access memory out of bound, and this is a problem. This kind of bug, type confusion, have been found in big C++ projects, namely Chromium and Firefox in these recent years. In our work, Type++, we present a new C++ dialect that is free by design of derived type confusion. A dialect is a small modification from a main language. I'm Swiss, and half of my country speak Swiss German, which is a slight deviation from the High German spoken in Germany. So there's a few changes, but the syntax and the overall structure stays the same. Our goal with this dialect is to be able to type check every derived cast throughout the program. For that, we need every object to have a type associated with it throughout its lifetime. How do we do that? Basically, we add type information to every object, every classes that are involved at some point in a derived cast. We do that through RTTI, runtime type information, that is readily available in C++, but is reserved to polymorphic types, and we extend that to all the types that are involved in derived cast. This changes poses two questions, or has two implications. First, it slightly changed the object layout. I'll come back to that later. And second, we need to actually initialize this type information. As we use inline type information, it's the only point in the object lifetime that we care about, but we need to make sure that at object creation, the right type is put into this type information. How do we do that? It's quite basic. We just rely on the default constructor. We make sure that a default constructor is defined for every classes that we instrument. If it's not the case, we transparently define one. And then we just rely at object creation on this constructor to be called. If you use a new keyword, as you should, this is not a problem. It automatically calls a constructor. But if you rely on C-style allocator, malloc, calloc, or realloc, we explicitly add a call to the constructor. We carefully handle calloc and realloc. So for calloc, we make sure that every object actually allocated will have his type information set. For realloc, we make sure that we only call the constructor on the newly allocated memory. Additionally, we have an allow list for custom memory allocators to make sure that we set the type information at the right place. So if you have a pool allocator, for example, or if you use ASAN, so the kind of allocator that add extra metadata on top of the object. Coming back to the actual layout changes, as we add this RTTI to the object, we slightly change the object layout. This is defined in the C++ ABI, and it means that we slightly break it. We handle it in two different ways. First, we have automatic ways to handle, for example, if you use external libraries. These libraries will not expect your object to have this type information. Therefore, we have wrappers that allows you to remove this type information and transmit the object without it to the external libraries. Additionally, if you have, for example, a header that is defined in C and C++ code, we have macros that make sure that the C code is aware that there is some extra field containing the type information. Then, sadly, there is still some code that is incompatible with our dialect. For this, we have a comprehensive static analysis that provide warnings about this location, allowing the developer to look at them and possibly adapt them. In practice, though, these cases are quite limited. On the Spec CPU benchmark 2006 and 2017, it's less than 0.04% of the code, and usually in code segment that will actually greatly benefit from modernization. Coming back, let's speak a bit more about the incompatible idioms. The first one I want to discuss a bit is comparison with size-of. As you probably know, size-of returns the size of the object. This is actually what we want, because we want the size to actually have the type information. So as the value might change between C++ and type++, it means that the new size might be different in type++ than in C++. For malloc, that's fine. You actually want this type, this new size. But if you have a comparison with a scalar value, for example, this will be problematic. This is also code that is not always portable, so that is also a reason why we encourage the developer to adapt this code. The second idioms I want to discuss a bit more is what we refer to as implicit placement new. If you look at the bottom code snippet here, the developer defined two classes, X and Y, and it will use them interchangeably at a later point in the program. It defines first the class X with different fields, and then it defines Y as a char array with the same size as X. However, when you use this idiom in type++, you will have a type information field in X, but you will also have one in Y. But since Y has a char array with the size of X, it will have a second space for extra type information. This means that when you do the cast, which is actually a type confusion, this will be problematic because the fields will be offset by the type information part of the Y object. Again, you can do that with more modern idioms that is less problematic. Our evaluation, we first wanted to look at one aspect, which is the porting effort. So if you want to move from C++ to type++, how much work do you need to do? To do that, we look at the Spec CPU benchmark, we look at the 16 C++ programs, and first run our static analysis on them. It reported 179 warnings, and after looking at them, we had to modify 314 lines of code. Again, really few in comparison with the 2 million line of code of the benchmark. One example that we had to modify is Blender that was relying on undefined behavior. Basically, they wanted to store the type of an object, and they were doing it through tagged pointers, so storing it in the least significant bits. This was problematic because when there was a cast, we wanted to do a type check, and we were not able to find the RTTI because the address was unaligned. Luckily, if you use type++, you can remove these idioms because you actually have type information in all these objects. The second aspect we wanted to evaluate is security and performance. Type++ protects many more casts than previous sanitizer. So hex type, for example, is the state of the art, protects around a bit less than 6 billion casts. In comparison, type++ is able to protect 90 billion casts if you look at the top table. And all of that with a much lower overhead. So type++ experience an average of 8% extra overhead, while type++ is more in range with the state-of-the-art mitigation, LLVM CFI, the middle column here, which is also at less than 1%. This shows that actually type++ and runtime type checks are actually quite cheap, and you should actually use them in your programs. If you look at the maximum overhead, we are less than 5%, and it's more or less scaled with the number of casts that are actually done. and more importantly, also with the number of type confusion, which are more costly. The last part of our evaluation was a case study of the Chromium project. This is a huge project. I was a single PhD student, so we were not able to port it completely, but we expect the software team at Google to be able to do that more effectively. We ported already 92% of the classes that need instrumentation, and we already looked at the 3,000 warnings that were outputted for them and fixed 230 lines of code. One adaptation that was necessary was in the Protoc, the protobuf compiler of Google, that was actually outputting some comparison with a strict size of classes, and that was incompatible with Type++. When we ran this protected binary, we experiences less than 2% overhead on the JavaScript Jetstream 2 benchmark. Overall, we already protect 90% of the cast, double as many casts as LLVM CFI. To conclude, Type++ is a new C++ dialect that protects derived cast by design. By adding runtime type information to every classes involving derived cast, we are able to do runtime check throughout the object lifetime. This comes at a slight cost because we changed the ABI, but in practice, it is a limited number of lines of code that need to be patched. But after that, you have a binary that is fully protected from type confusion in derived cast. In practice, when you deploy it, we experience less than 1% overhead while protecting already 90 billion cast, 23 times more than the state-of-the-art mitigation. We identified 14 new type confusion in the spec CPU benchmark. And if you want to have a deeper look at our paper, it's available on our group homepage. And the artifact is also available and evaluated by the NDSS artifact committee. Thank you for that, on GitHub. And with that, I'm happy to take on questions.
Are there questions from the room? Please come here to the mic. In the meantime, I'm going to warm up the question time. I'm curious. This is a very interesting and relevant topic for the the implication that it has. So, what prevented you from being able to tackle also the unrelated casts? How much difficulty is there to solve?
So, unrelated casts are casts from void star, for example, or from two classes that are not related. It's more or less much more extra work. Does anybody have water that I can have? Anyway, no. Unrelated cast, there is much more classes to instrument, which means much more classes to patch. This is just a lot more work to look at the warnings and patch, and there's might be also extra overhead because you change many more object layout having an impact on the cache.
I'll follow up on that. I was wondering, of course, this is necessary for having perfect detection, but in some cases you might, will the size of the objects be a good proxy? Like there is one work that I have in mind where they face this problem in C, where they, like in the Linux kernel, there's this container of method that you can simulate inheritance and do upcast, downcast.
Yep.
So in that case, they might still have false negatives, but the size is a good predictor of whether the cast is legitimate or not. So this might be something that you might consider for having limited slowdowns.
Yeah, so there is some static analysis that you can do to already see if the cast is likely to fail or not. So yeah, that will be interesting.
Okay, so if there are no more questions, let's thank the speaker and we move to the second talk.